Our next speaker is Matei Zaharia. Matei is a graduate of a PhD here at Berkeley under Scott Schenker and Jan Stojka in the AMP lab. He's now assistant professor at MIT. He has the ACM Doctoral Dissertation Award from 2014, and he's the co-founder and CTO of Databricks, bringing you Spark. He and I share a degree of Bachelor of Mathematics, strange thing, from Waterloo.
Mm-hmm. Cool. Okay, well, thanks. So I'm really excited to be invited to give a talk here. Unlike Randy, I didn't know you can just change your title, so I actually stuck with the title that Dave assigned me. Yeah, I know. I'm learning a lot of things. So I stuck with the title that Dave assigned me, which is the future of big data. And I'm also going to take a chance to just talk about how the big data research worked at Berkeley under Dave's research model, because it's a really cool example of it. So basically, as far as I know from the time I was here, this is essentially what happened. The RAD lab, which was started in 2006, was created to manage large data centers. And as part of that, the faculty there were interacting with a lot of companies that operate data centers, and we're seeing a bunch of interesting things going on. And as part of that, we actually saw that data analytics came up as an emerging use case in more and more places. At first, there was this Hadoop thing, maybe a few people use it, and then suddenly everyone at the RAD Lab retreats was talking about Hadoop and MapReduce and big data. So then the AMP Lab was started essentially to solve the big data problem. And both are great examples of Dave's approach, where you pick an area that is emerging in industry, you stay in close touch with the people doing it there, and you still do extremely impactful research with a great team of people. So this was sort of my experience of the RAD Lab and some of the cool things that happened. So the first course I took was actually the kind of seminar that these labs organized. In my year, it was taught by Randy, and this was a course on architecture of internet data centers. And in that course, we actually played around with Hadoop, which was kind of coming up as a technology, as well as with cloud computing, Amazon EC2. And as far as we know, our group in the RAD Lab was one of the first to really use cloud computing in research, and perhaps also one of the first to actually use it for big data processing, such as Hadoop. Here's one reason why I think that, which is an experience we had working with Amazon early on that was pretty fun. This is one of our papers that we wrote. So we actually got Anthony Joseph's credit card. We got an Amazon EC2 account, and we just tried launching 800 VMs and running MapReduce on them. Very soon after doing that, we got a call from Amazon. This was early on, where they were saying, "Hey, what exactly is this computation you're running on these machines? It seems to be making a lot of network connections. It seems like maybe every one of those 800 machines is trying to connect to every other one of those machines." And we said, "Oh yeah, it's MapReduce." And the answer, "Oh yeah, MapReduce. Yeah, that's interesting. I don't know. Let us look that up." So we had for this first paper, we actually got put by Amazon into this sort of test environment and got to run our computation there, because the infrastructure in production actually had a bug at the time that couldn't let it run it. This was some of the first research that studied both MapReduce and cloud computing, and it turned out to be like a really great set of topics to look at. And all of it came out of having that course and having that connection through the RAD Lab with companies that were using data centers and seeing what they were kind of moving towards. So as a result of the interest in cloud, the RAD Lab and AMP Lab did a lot more work on cloud computing. We put together, Dave led this paper that one or two people somewhere have read. We also started doing these open source big data systems. So here's a picture from the AMP camp, which is kind of a one-day workshop we organized for industry folks to use the AMP Lab systems, such as Mesos and Spark, to try them out. And as soon as we hosted this and we had people come there, we started seeing a whole bunch of open source users and a bunch of companies start to use it. So it was a really cool environment to be working in, both seeing these kind of trends early on and having the connections with the people at the companies doing these to actually get feedback from them and influence what they're doing. Okay, but in this talk, I'm also supposed to talk about future of big data, and so I'm going to split that up by talking about a few different aspects, and I'll start with future big data systems. What are the systems challenges there? So one cool thing, like in everything in computing, a lot has changed since 2010 when we started the AMP Lab, and a lot of the trends in hardware, as Dave has pointed out so many times, then directly affect software and even applications, after a few years. So basically, when we started, when at least our group started looking at big data, we were in a world like this, where you had servers with mostly hard disks, and you had pretty slow networks, around 1 gigabit per second, pretty slow compared to the speed of the processors on those servers. And so the name of the game was to minimize I/O and minimize network communication, maximize data locality, and that's how you got high performance for big data. That's kind of everything we did. Now, if you look a few years later, in 2016, storage has gotten a lot faster. You can have SSDs that are increasingly becoming a common way to store that. Networks have gotten at least 10 times faster, and the most commonly deployed ones in data centers. They're also now usually full bisection bandwidth. And CPUs, unfortunately, are still roughly the same speed. So basically, these two things improved by a factor of 10, CPUs didn't. So one interesting thing that we're seeing happen is that actually CPU, which wasn't really optimized for much in the early systems, is now the bottleneck in systems like Hadoop, Spark, and a whole bunch of other big data systems. So that's kind of an interesting thing. That means you have to bring out techniques both from software, maybe also from architecture, to make good systems for these kind of problems. And these trends are likely to continue. On the storage side, there's a lot happening that will give you pretty big, fast storage. Things like SSD prices falling. It's projected that they will soon fall below hard disks if you include the total cost of sort of managing and powering them. Also, non-volatile memories such as 3D XPoint. And Ethernet continues to improve very quickly, so pretty soon we'll have another 10 times speed up in Ethernet very widely deployed. So I think the result of this on the system side is two things. Big data engines will need to be compute optimized. This is pretty hard given that a lot of the current systems use pretty high level kind of languages and interfaces, things like Java or Python. But it means that you can really get a significant speed up by optimizing these for the CPU. And also we'll need new storage systems and maybe even new compute systems that take advantage of the new storage hierarchy. And we're starting to see a few examples like this in the open source world. So just two examples I'm aware of. One is in Spark. A lot of the work lately has been actually on optimizing CPU efficiency. There's this thing called Project Tungsten, which tries to generate code at runtime. Right now it's Java code, but eventually it will probably be native code from SQL and from the other APIs. So this is now the most important thing. And the other thing is in storage systems. So Luxio, which started out as Tachyon in the AMP Lab, is an example of a storage layer that just optimizes for caching and DRAM and flash, because 99% of the data you access can probably fit in these faster storage media. And these don't look like the systems that were there even 5 years ago. So these are, I think, kind of the biggest changes in systems. Another exciting thing to look at is future users of big data, and that will also affect what happens out there. And this is also a place where I think there's a lot of change. The first big data systems were really targeted at programmers. They were developed at places like Google, where the vast, the kind of majority of employees who would use these are software engineers. They have a degree in computer science probably, and they're sitting there programming. And this is for, if you're a Java programmer or a C++ programmer, you can now write stuff on a bunch of machines. But increasingly, big data is used by non-programmers, either in scripting languages, by people like statisticians or scientists whose primary education isn't in programming, or even in visual tools. And as an example of like a really dramatic kind of effect of that, I have a little graph here with the usage of various languages in Apache Spark. So when Spark started out, it only supported Scala, which is a language basically for software engineers. And even after we added a Python and R interfaces, for example, the vast majority of usage was in Scala and Java. And then in the past few years, we've slowly seen the other scripting languages creep up and kind of overtake some of the languages used by developers. So when we did this survey last year, Python jumped from, I think it was 30% the year before to close to 60% now. And R, which is a language that we only added, I think, 1.5 years ago, also jumped to close to 20%. At Databricks, where we host this cloud-based Spark platform, Python is actually even more popular than Scala among sort of our users. So it's very interesting to see this because they're a different type of user and they expect and kind of require different interfaces to work with this. So something that worked for Java programmers is unlikely to work for these ones. So the result of that is that there's a big need for easier interfaces to big data, ideally ones that look like the single machine tools that users are familiar with, which definitely don't look like MapReduce or like the original Spark API. And there's a lot of really cool activity happening here, including a lot of research in the AMP Lab and at Berkeley. So some examples are Spark data frames that use a popular kind of data science API, the IPython notebook, the Caffe machine learning library for hooking together learning pipelines, and visual interfaces like Tableau. And I think there's still a lot to be done to really connect these with the big data systems and make them work well. Tell users what's really happening and how can they improve their applications. So this is another area that I think will be interesting to look at. And the final thing I want to talk about is future applications of big data. And this is also a place that I think is really exciting. So basically, what I believe here, I think, and a lot of people believe, is that the most impactful applications of big data for society are still nascent. They're still very early on. And these really impactful ones are things like large-scale science, using big data tools to understand scientific data around us, personalized medicine, in general, using all the information we can sense about a patient to actually design really great therapy for them, and also civil applications. So can you use it to improve, cities, as Randy was talking about? Can you use it to monitor transparency? Can you use it to actually improve society? Because there's now a lot of data available that could come in to do that. So as one example of this that I think is really a great example that started in the AMP Lab is the AMP Lab genomics effort that was led by Dave. So we became interested in genomics because we started talking early on with for example, various medical researchers that wanted to use our big data tools. And we put together, or I should say Dave put together, a group of people from 5 different institutions. We had the AMP Lab, Microsoft Research, UC San Francisco, and later OHSU in Oregon, and also UC Santa Cruz. And this group had a lot of great discussions and a lot of really interesting impact on a bunch of the real medical and scientific applications these were doing. One of the things that happened very early on that shows how impactful this will be is Dave's article in the New York Times on computer scientists may have what it takes to help cure cancer. And basically his argument was that if computer scientists actually have some of the skills required for this, aren't we actually obligated to do it if it can have so much impact on the lives of people? And it's obviously a big goal to try to do this, but I think the things that happened in this effort actually took some meaningful steps towards that. So just this effort, which I think started probably in 2012 or 2013, it's pretty recent, already has led to a lot of really great software. So for example, Atom is a toolkit for genomic data processing that came out of the AMP lab, where basically they said, let's take the file formats and processing systems that are industry standard in places like Hadoop, and let's just put genomic data in them. And when you did that, you actually could make the data a lot smaller. It actually compressed better than the specially tailored formats that biologists use themselves, just by putting it into a standard Hadoop data format. And you could also operate on it a lot quicker. And Atom is used in a bunch of other projects now at different research institutions. SNAP was a high-speed sequence aligner that actually I also helped work on that was used for things like identifying new pathogens and also building new pipelines, for example, for sequencing RNA. And Avocado is a distributed variant caller based on Atom that can do the main computational task in sequencing a human genome a lot faster. And another thing that I recently learned in this area is that the Bose Institute's GATK, which is the most widely used pipeline for genomic data processing, now uses some of this AMP technology. It actually, for example, they're changing the GATK to run over Spark in parallel. So it's really cool to see other groups using this technology as well. Okay. So just to conclude, the AMP lab, when the AMP lab defined big data, it was actually a pretty interesting definition, kind of a moving goalpost definition. Basically, the definition is that it's data or problems that are too difficult for current techniques to handle. So it seems like something where, if the lab is truly successful, then there'll be no more big data anymore. But fortunately for researchers, at least, even with this definition, there's still a lot of big data out there. And I think now that a lot of the basic infrastructure is in place, there's space to really work on these super impactful applications like the genomics ones, and to connect with, with practitioners in other fields. And the model of collaboration with industry and research in these kind of diverse groups of PIs that stay well connected to it has worked extremely well in it. And I hope it continues to work really well to have academic impact in this field. Thanks.
Questions? I have a question. So when I first read about Spark and RDDs, I saw a lot of emphasis on the performance advantage over Hadoop.
Yeah.
And now you're putting a lot of emphasis on the ease of programming. How do you see the balance between these two?
Yeah, that's a really good question. Actually, if you go back to my system side, I said, programming these things in Java and Python isn't going to work anymore because they're now CPU bound. So I think that's a really difficult tension. To be honest, even though I really like performance as a systems person, I think ease of use matters more basically. So I think in all cases, we've prioritized ease of use basically because actually this is a thing John Auster had said is the biggest performance improvement is when you go from not working to working. So this is, at least in Spark, this is what we've done. But I think it's a really interesting tension and a lot of options can come in to improve that. Yeah.
Great talk, and love the enthusiasm, and particularly agree with your notion that the most impactful applications are still ahead of us. They're still nascent, so we have a lot of room as a community to go impact the world still. I'd love to hear a little bit about some of the new projects you're doing at MIT. Could you maybe say something about one or two of those?
Okay, yeah. I don't have slides on these here, but definitely this problem, the kind of the hardware trends problem, is one of the ones that we've been looking at. So basically, we've tried, we measured a whole lot of big data systems, not just things like Spark and Hadoop, but even databases, machine learning toolkits like Caffe or TensorFlow and things like that. And a lot of them perform kind of much worse than hand-tuned code for this stuff. And I'm not talking about like spending months tuning the code. I'm talking, spending a couple of days, by a student who's aware of performance. So one of the projects we're trying to do is actually kind of this low-level intermediate language that can express a lot of data parallel computation and makes it very easy to compile to fast code. So basically the idea is we could take a lot of the APIs in Spark or a lot of the things that are needed to run SQL and run them on this kind of hardware. And it's still early on, but I think there's space to do a lot of stuff here, mostly because the gap is so big. And this is done, what we're doing now is without changing the user interfaces to these libraries, just making it easier for whoever writes Spark or whoever writes a database to get fast code. So this is one of the things.
I had a question about this, actually about this specific slide.
Yeah.
Which is that even though the clock rates have been flat since 2002, we still are seeing performance improvement, except it's the number of cores. So does that factor in at all?
Yeah, that's a good point. Yeah, so there are more cores, although it's not a factor of 10 more compared to back then. I think, I actually don't know exactly, but I'd say maybe more like a factor of 4. So that is true. But even if you look at the number of cores, the processing kind of capability isn't keeping up with I/O as well as it did before. And of course, these are also hard to use. That's a different problem. Yeah.
Thank the speaker.
All right, thanks.